Welcome back to the computer lessons.
Silicon processors do not understand high-level code. They understand only a specific command dictionary called an instruction set architecture. This architecture defines how software talks to silicon, determining the efficiency and speed of every calculation. Today, a war is raging between two different design philosophies, x86 and ARM. The x86 architecture is the veteran of the desktop world, tracing its lineage back to the Intel 8086 processor released in the late 1970s. It was built during an era where memory was expensive and programmers wanted to do much with a single command. This led to CISC, or Complex Instruction Set Computing. In a CISC environment, a single instruction can perform multiple operations, such as loading data from memory, performing an addition, and storing it back. Think of it as a heavy, multi-purpose tool that can do several jobs but requires significant energy to lift. This allows software to be compact, saving precious memory space. However, this complexity comes at a significant physical cost inside the silicon itself. Because instructions vary in length, the CPU must dedicate massive amounts of space to decoders that translate these commands into simpler micro-operations. These decoders consume power and generate heat before the actual calculation even begins, creating an efficiency ceiling. Opposite this stands ARM, which began as the Acorn RISC machine in the 1980s. ARM represents the RISC philosophy, or reduced instruction set computing. Instead of complex instructions, RISC uses a small set of simple, uniform commands that each perform one task. It is a philosophy of speed through simplicity. In an ARM processor, every instruction is the same length, making the decoding process fast and efficient. Because the chip doesn't need massive decoders, more silicon space can be dedicated to actual cores or energy-saving features. This architectural simplicity is the reason why ARM chips consume less power than their x86 counterparts. Imagine a chef in a kitchen. A CISC chef has a specialized machine that makes a whole sandwich with one button, but it is huge and uses lots of electricity. The RISC chef has a simple knife and does every step manually but works at lightning speed. For decades, these chefs lived in different worlds. x86 became the absolute king of the desktop and server markets because raw power was more important than battery life. When your computer is plugged into a wall, you don't care if the processor is inefficient. Intel and AMD pushed x86 to its limits, creating multi-core monsters that handle the heaviest professional workloads. But then, the world shifted toward mobility. When the smartphone revolution began, the primary constraint was no longer raw speed, but the limited chemistry of lithium-ion batteries. An x86 processor in a pocket would drain a battery in minutes. ARM was perfectly positioned to dominate this new era of ultra-portable computing devices. This created a massive divide in the software ecosystem. Programs written for x86 cannot run natively on ARM because they speak a different mathematical language. This is why you couldn't run Windows on your phone for many years. The hardware walls were too high for software to climb without losing significant performance. One of the most significant technical differences is how these chips handle memory access. x86 utilizes a complex approach where instructions interact with memory directly. ARM uses a load-store architecture, meaning it must move data into internal registers first. This predictable data flow allows ARM to optimize its pipelines for maximum energy efficiency. The business models of these giants are also fundamentally different. Intel and AMD manufacture their own physical chips, keeping secrets locked inside their factories. In contrast, ARM Holdings does not manufacture a single processor. They only design the blueprint and license it to other companies like Apple, Samsung, and Qualcomm for customization. This licensing model allowed for the rise of the system on a chip, or SoC. Because companies could customize the ARM design, they started integrating the CPU, GPU, and RAM onto a single piece of silicon. This integration further reduced power consumption and latency, making modern smartphones as powerful as many older laptops. For a long time, x86 was safe in the high-performance market because ARM was seen as weak. People assumed that RISC architectures could never handle video editing or gaming. But then, Apple changed the industry with the M1 chip. They proved that a high-performance ARM design could actually outperform traditional x86 desktop processors. Apple's success relied on a technical miracle called Rosetta 2. This translation layer converted x86 instructions into ARM instructions in real time. Because the ARM hardware was so fast, it could run translated x86 apps faster than many native x86 machines. This demolished the software wall and proved that the transition was finally possible. Now, the battle has moved into the data center. Cloud giants like Amazon and Google are building their own custom ARM-based processors, such as Graviton. When you run thousands of servers, electricity is your biggest cost. If an ARM server does the same work for less power, it saves billions and reduces environmental impact. x86 is not standing still. To fight back, Intel and AMD have adopted a hybrid architecture strategy. Modern x86 chips now contain two types of cores: performance cores for maximum power and efficiency cores for background tasks. They are essentially trying to make x86 behave more like ARM to save energy. This hybrid approach requires the operating system to be much smarter. The thread director in Windows must now decide which apps go to which cores in real time. If it makes a mistake and puts a game on an efficiency core, performance plummets. This management is the cost of trying to modernize the legacy architecture. Thermal management remains the ultimate deciding factor in this war. A processor's clock speed is limited by how much heat it can dissipate before silicon degrades. ARM's efficiency means it produces less waste heat. This allows ARM devices to stay thinner and avoid the loud cooling fans that are still common on x86 laptops. Beyond ARM and x86, a new challenger called RISC-V is gaining momentum. While ARM is a licensed proprietary design, RISC-V is fully open source. This means any company can use the architecture for free without paying royalties. This open philosophy could eventually disrupt both ARM and x86 by democratizing the future of chip design. We must also consider the role of the manufacturing process, known as the node size. Companies like TSMC are now producing chips at 3 and 2 nanometer scales. These microscopic transistors allow ARM designs to push higher clock speeds while maintaining an efficiency lead. The smaller the transistor, the less energy it takes to flip a switch. Specialized workloads like artificial intelligence are creating a new battlefield for these architectures. Modern ARM chips often include dedicated neural engines to handle matrix math. While x86 chips are adding similar features, the modular nature of ARM makes it easier for designers to bolt on specialized accelerators for specific tasks like image recognition. Compatibility remains the last strong fortress for the x86 architecture in the corporate world. Many critical business applications and legacy systems were written decades ago specifically for Intel hardware. Moving these systems is a massive risk. This keeps x86 alive in the enterprise market despite its efficiency disadvantages. In the gaming world, the transition is slow but steady. While powerful gaming desktops still rely on x86 and high-wattage power supplies, handheld consoles are shifting. The Nintendo Switch and many new portable devices use ARM because it is the only way to deliver quality graphics in a battery-powered form factor without melting the case. The future of computing is likely not a total victory for one side, but a world of heterogeneous computing. We will see machines that use x86 for raw strength and ARM for always-on connectivity. The architecture that wins will be the one that manages the most data with the least amount of thermal waste globally. Understanding this war helps you choose the right tool for your specific digital needs. If you need a workstation that runs for 20 hours on a charge, you are looking for ARM. If you need a gaming rig that pushes absolute limits, x86 still holds the crown. The silicon battle continues to evolve. We have analyzed the logic and architecture of the chips that think for us. But even the most efficient ARM processor is useless if it doesn't have a reliable source of chemical energy. In our next video, we will dive into the chemistry of lithium-ion batteries to understand how we store the electricity that powers our world.
The transition from x86 to ARM represents a massive shift in history since the move from vacuum tubes to transistors. Do you believe that x86 will eventually disappear from our desks, or will it always be needed for the heaviest professional tasks? Share your thoughts on the future of processor design in the comments below. If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.